Hi guys, very good morning. Welcome to the session. So morning sessions are always very good. I like morning sessions because the focus will be wonderful in morning sessions especially. So we are going to talk about a very important topic today, Laplace transform and region of convergence. So region of convergence is the crux of Laplace transform. So the most important thing about Laplace transform is region of convergence, which we have to understand very carefully. Okay. So I think my audio and video are clear, right? Yes. Right. So we're going to understand each and every bit of what should be understood regarding Laplace transform and region of convergence. And we're going to build on those things in further classes. So for the next 6 classes, I'm going to talk about only Laplace transforms. So in today's class, we're going to talk about region of convergence. So we're going to talk about from the very basic. So assuming that you don't know anything, I'm going to start. So this is my profile. So I teach communication systems, signals and systems. So this is my Telegram group. So if you wish to ask me any doubts, you can contact me in this group. Right. So let's start. So what is the agenda of today's session? What all we are going to discuss in today's session? Let me quickly tell you that. So first we're going to talk about bilateral Laplace transform, unilateral Laplace transform. So we generally hear about only Laplace transform, but there are two types of Laplace transforms. One is bilateral, second one is unilateral. Okay. So we'll talk about what is the difference between them. So Fourier series and Fourier transform. So we learn these topics, Laplace transform, Fourier series, Fourier transform. We learn them in signals and systems as well as in mathematics. So I'm teaching as a signals and systems teacher. So whatever you have learned in mathematics and signals and systems, is it same or is it different? So I'll tell you that. Okay. So what transforms are exactly same in mathematics and signals? What topics are slightly different? So where you should be careful, I'll talk about that. Second thing. So we'll talk about quickly talk about Fourier transform, Laplace transform formula, using which we'll talk about the condition for well-defined Fourier transform. So I've discussed this in very detail in Fourier transform topic, which I've covered in last month. So I'll just revise this part because that we have to use it in understanding the region of convergence of Laplace transform. Okay, right, and we'll understand whatever things that should be understood regarding ROC of Laplace transform and why. What is the reason why we call it as a region of convergence? We'll talk about that as well. And at the end, I'll give you a few homework questions based on whatever is discussed in today's session. So you can solve them and post it in the comment section if you are able to answer them. Okay. Hi Dreamer, what is your name? Right. So coming to this transforms, we learned this bilateral, unilateral, we learned Laplace transforms, Fourier series and Fourier transform. These three topics are common between signals and systems and mathematics, right? So Laplace transform that we learn in mathematics and Laplace transform that we learn in signal system, it is not same, it is different. And what is the difference? The thing that we learn in mathematics is unilateral Laplace transform. Mind this, the Laplace transform that we learn in mathematics is unilateral Laplace transform. Though specifically they may not mention it, they just say Laplace transform, but the Laplace transform that they talk about is unilateral Laplace transform. And the Laplace transform that we learn in signals and systems is bilateral Laplace transform. What is the difference? We'll talk about that. So the Laplace transform that we learn in mathematics and signals and systems is different. Okay, so whatever formula you remember or you might have learned in mathematics may not be exactly same as that you learn in signals and systems, but some of them are same, some of them are not same. Okay, for what cases the formulas will be same in unilateral and bilateral, for what cases it will be different, we'll talk about that as well in the next slides. Okay, so this is just an introduction slide. Next, Fourier transform and Fourier series that we learn in mathematics and signals and systems are exactly same. There is no difference. So Fourier series, Fourier transform wise, whatever formulas or whatever you remember in mathematics, it is exactly same in signals and systems also. But in signals and systems, we explore it in little bit more detail. We go more conceptually by applying it to systems and all that. In mathematics, you just do it like mathematical formula. You just go ahead with the like mathematical formulas. But in signal systems, we try to learn the meaning behind it also, how it is applicable also. Okay, but these two transforms, these two things are exactly same in mathematics and signal systems. So whatever you remember in mathematics, that is applicable for signals and systems also for these two topics. Okay. Yeah. Hi, Rahul. So any doubts till this point? I've just, I'm talking about this is just intro part. Any doubts till this point? Come on, respond quickly. If you're not getting doubts, means either you should have understood completely or you have not understood anything. If you're in between, you should have doubts, definitely. Okay, let's assume that you have understood everything. Okay. Right, let me go to the next slide. Let me explain few more things. Okay. So I'll discuss the Laplace transform and Fourier transform formula. First, let me give you Fourier transform formula, okay? You might be already knowing it. So let me change the color. X of omega is equal to integration of x of t into e power minus j omega t dt. Limits from minus infinity to plus infinity. This is the Fourier transform formula for a signal x of t. This is the formula that we use to find the Fourier transform of a signal x of t. And we don't use this formula always if x of t is absolutely integrable. Only then we use this formula. Otherwise, we can't use this formula. I've talked about this in detail in my Fourier transform sessions that I've taken in the last months. Okay. So under this condition, only if x of t is absolutely integrable, only then we can use this formula to find Fourier transform. So what is absolute integrability? If you take the absolute value of the signal or modulus of the signal and then integrate it for all values of time, or it's as simple as saying finding the area of the signal, not exactly the area of the signal, finding the area of the modulus of the signal. Take the modulus of the signal for that signal. Modulus, when you take modulus, what happens? The negative values also will become positive values. For that signal, for the absolute value of the signal or modulus of the signal, if you find the area, that should be finite. Finite means anything, any value other than infinity. Any value other than infinity. If a signal satisfies this condition, we call it as absolutely integrable. Only if the signal is absolutely integrable, we can use this formula to find Fourier transform. Okay. Now let us quickly learn the Laplace transform formula. Sir, Laplace transform means just now you told bilateral and unilateral. What Laplace transform are you talking about? Yes, let's talk about both of them. Let's talk about bilateral Laplace transform. Bilateral Laplace transform. Bilateral Laplace transform of x of t. Okay, implies the notation is capital X of s. The capital letter is used for representing Laplace transform or Fourier transform. So capital X of s represents the Laplace transform of signal x of t. The formula goes like this: integration of x of t into it looks exactly same as Fourier transform formula. Only thing is, in place of j omega we'll have s. In place of j omega we'll have s dt, where limits run from minus infinity to plus infinity, which means we are gonna do this integration for all values of time from minus infinity to plus infinity. Right. Sir, is s same as j omega? If s and j omega are exactly same, if s is equal to j omega, then Fourier transform and Laplace transform, there is no difference. Right? But there is a difference, no? There should be a difference. Otherwise, why will we learn about Laplace transform separately? If s and j omega are same, then Fourier transform and Laplace transform are exactly same. Then there is no point of learning two different things. Two things which are same under different names, right? So why we are learning it as different thing is because s and j omega, they are not same. But what is s value? S is not just j omega, it is sigma plus j omega. It is sigma plus j omega. So there is some real part also. Sigma plus j omega. But if you put sigma equal to 0, then Fourier transform becomes Laplace transform. Okay. Right. We'll talk more about this. Under what conditions we can substitute sigma equal to 0. We have to understand that as well. Okay. So this sigma is a real part of S. And this omega is imaginary part of S. So S is a variable here in Laplace transforms. Okay. Similarly, let us talk about unilateral Laplace transform that you use in mathematics. Unilateral Laplace transform of x of t. So what is the formula for this? The notation is same for unilateral Laplace transform also. We use the capital letter and the variable is s. Formula is also almost same. Only one change in the formula between unilateral and bilateral Laplace transform. There's only one small change. Upper limit is same, but the lower limit is 0. What is the meaning of this? And here also S is sigma plus j omega. Okay, understand this carefully. What is the difference? The lower limit is different. So you are trying to evaluate the integral in bilateral Laplace transform for all values of time, positive time as well as negative time. Whereas in unilateral Laplace transform, you are trying to evaluate the integral only for positive time. That is the only difference. That is the only difference. Observe this carefully. Here we are integrating only for positive time. Here we are integrating for all time. The name says, as the name says, bilateral, unilateral. Uni means one. Only positive time. Uni means only for positive time. Bilateral means both. Both for positive time as well as negative time. We are evaluating the integral both for positive and negative time. That's what bilateral. Unilateral means only one side. We are evaluating only for positive time side. Okay. So that is the difference. I hope you are understanding the difference. Right. I hope it is clear till this point. So I have written Fourier transform formula, bilateral Laplace transform and unilateral Laplace transform formula just for you to observe what is the difference between those formulas. See this one, these two formulas look very similar except for one small change. Instead of j omega we are having s, and what is the s value? It is sigma plus j omega. Otherwise, apart from j omega replaced with s, everything else is same. Okay, and unilateral Laplace transform, it is almost same as bilateral Laplace transform formula except for the lower limit different. Okay, right. So now, understanding this, having understood this, let us find a relation between bilateral and unilateral Laplace transform. Okay. Okay. So don't look at these two conditions. We'll derive it. Okay. We'll derive it. X of s bilateral Laplace transform is equal to, I am writing it as b because I am talking about bilateral Laplace transform now. X of t into e power minus st dt. The limits are from minus infinity to plus infinity. Shall we write it as integration from minus infinity to 0 x of t into e power minus st dt? Is it okay? I'm separating the integration into two parts. One integration from minus infinity to 0 and the second one from 0 to infinity. See this? I hope this part should be easy to understand. I'm just writing this integral. I'm just dividing this integral into two parts just by dividing the limits into two parts. Okay. Hi Vaibhav. Good morning. So I hope this part is clear. So is it not looking like unilateral Laplace transform? Bilateral Laplace transform is equal to integration from minus infinity to 0 x of t into e power minus st dt. Don't look at these two statements. You can look at these two statements after understanding this, because here we're going to understand, we're going to derive these two statements. Okay. Next up, is it not looking like unilateral Laplace transform? It is looking like unilateral Laplace transform. Let me go back to the previous slide. See this one, unilateral Laplace transform formula. This is bilateral Laplace transform formula. In this slide, bilateral Laplace transform formula I have taken and I have divided it into two parts. In that one part is exactly same as unilateral Laplace transform formula. Correct? Now, under what conditions these two will be same? Under what conditions these two will be different? Let's try to analyze. U means unilateral Laplace transform, B means bilateral Laplace transform. Because we are trying to use both the Laplace transform in a single equation. That's why I'm showing the difference by using B for bilateral Laplace transform and U for unilateral Laplace transform. Right. Under what conditions are these two same? If x of t is 0 for negative time. See this one? So this is evaluation for negative time. If x of t is not there for negative time. For positive time, what is its equation? It does not matter for us. For negative time, if it is not existing, for what I mean by that is, whatever is its shape in the positive time, for negative time it is not existing. For negative time it is 0 amplitude. For all negative values of time, it is having 0 amplitude. For positive values of time, it can have any shape. That is what I mean by this. If this happens, then what happens is bilateral Laplace transform is equal to, if x of t is 0 for negative values of time, this part becomes 0. Then bilateral Laplace transform and unilateral Laplace transform becomes exactly same. See this? So for what signals? The formula that you have learnt in mathematics and signals and systems is exactly same as, because in mathematics you remember the formulas of unilateral Laplace transform, whereas in the signals and systems you learn about bilateral Laplace transform. Though they don't mention that word bilateral and unilateral explicitly, but you are learning two different things. But the formulas are same if you are talking about signals which exist only for positive time. If you are talking about signals which exist only for positive time, or causal signals, you can say. So bilateral Laplace transform and unilateral Laplace transform are same for causal signals. Can I say that? Causal signals means signals which exist only for positive time. Right? So if x of t is not 0 for some values of negative time, for at least one value of negative time, if x of t is not 0, then what? This part will not become 0. If this part will not become 0, these two will not be equal. So bilateral Laplace transform is not same as unilateral Laplace transform for non-causal signals. So the formulas that you have learned in mathematics and signals are same for causal signals. For non-causal signals, they are different. Sometimes you will find, when you are learning signals, many times I've observed students, sir, this is the formula. This formula is different from what I've learned in mathematics. They'll say, okay. The difference is because the difference in formula exists only if you're talking about signals which are non-causal signals. Okay. If you want, you can go and observe. We'll talk about those signals in further classes as well. For example, whatever formula you learn for cos 80 in mathematics is same as unilateral Laplace transform of cos 80, and whatever Laplace transform formula you learn in signals system, which is bilateral Laplace transform, it is not for the same signal, it is for cos 80 into u of t. The formula in mathematics for cos 80 and formula in signal systems for cos 80 into u of t, they are same. Okay, because bilateral Laplace transform of cos 80 does not exist. It does not exist. Why it does not exist? We'll talk about that. We have not yet entered the actual topic. We'll talk about all of them. All these details you'll learn, but wait for some time. So I hope you have understood the difference. Under what conditions unilateral Laplace transform and bilateral Laplace transform is same? For the same signal. For same signal, unilateral Laplace transform you can find and bilateral Laplace transform also you can find. Those two will be same if you're talking about causal signals. And if you're talking about non-causal signals, for non-causal signals, this part will not become 0. That's why unilateral Laplace transform and bilateral Laplace transform will be entirely different. Okay. Causal signals means the signals which exist only for positive time. U of t minus 2, r of t minus 3. Okay. E power minus 80 into u of t. Any signal multiplied with the u of t or shifted versions, right side shifted versions of u of t. The signals which exist only for positive time, we call them as causal signals. If the signal is existing for a negative time also, then we call it as non-causal signals. Okay? No, causal signals need not be periodic. These two are entirely different things. Causality and periodicity, they are entirely different. Periodic we say when the signal is repeating. Causal we say whether it is repeating or not. If it exists only for positive time, if it should disappear, the signal should not be existing for negative time. For negative time, you should not be seeing anything. Here you should not be seeing anything. Before time 0, you should not be seeing anything. Only then we can call it as causal signal. there is no relation between means periodicity and causality. They are entirely different things. But periodic signals means always they are non-causal. Periodic signals can never be causal. Because periodic means it should repeat from minus infinity to plus infinity, which means they exist for negative time. So periodic signals are always non-causal. Okay, now read these statements. Bilateral Laplace transform and unilateral Laplace transform of a signal x of t are same if the signal x of t exists only for t greater than 0, or which is also same as only if the signal, if x of t signal is causal. Causality I am saying in this manner. So bilateral Laplace transform and unilateral Laplace transform of signal are different if the signal exists for negative time as well. They are different if the signal exists for negative time, which means if x of t is non-causal. Whatever we have learned here, whatever we have derived here, same thing I am putting in the form of statements here. Okay, I hope it is clear till this point. I am going a little slow. The reason is these topics are, these things are very, very important, and slightest confusion will not give you the confidence in the topic. Okay, we'll go faster when we learn all the basics. Okay, I'm moving to the next slide. Right. So whatever we are going to learn, what we are learning now, they are the building blocks. They are the foundation, which will help you to understand the next parts of Laplace transform. So condition for well-defined Fourier transform. So we have talked about this in my Fourier transform session, but I'm going to revise this in this slide. The reason is we have to use that condition for understanding ROC of Laplace transform. Okay. So let me first write the Fourier transform formula. X of omega is equal to integration of x of t into e power minus j omega t dt. Limits from minus infinity to plus infinity. So condition for well-defined Fourier transform. Before talking about condition for well-defined Fourier transform, you should understand what is well-defined. You should understand what is well-definedness of Fourier transform. Not only for Fourier transform, for anything. When you're talking about well-defined, it's properly defined values. Well-defined means it's other than undefined. What is the meaning of undefined? Undefined means plus or minus infinity values. Undefined values, what are those? There are only two undefined values, which is plus or minus infinity. These are undefined values, right? They are not properly defined. What exactly is the value of infinity? We know that it is very big. It is so big that there is no defined value for it. For example, 10 crores. If I say, we know it is one followed by 8 zeros. Okay, it's properly defined. What is the value of it? Okay, how big is it? It is properly defined. Like that, if you tell 1 lakh crores also, it is properly defined. It is very big, but it is properly defined. But infinity is so big that there is no value to define it. So these are undefined values. Well-defined is exactly opposite of undefined. Say, if you are talking about anything taking other than these values, if a signal takes other than these values, we can say they are well-defined. Okay, we can say that they are well-defined. Okay, so condition for well-defined Fourier transform. Well-defined Fourier transform means it means Fourier transform x of omega takes only finite values. Only finite. Finite means anything other than plus or minus infinity, we can call it as finite. Fourier transform x of omega takes only finite values for all values of omega. At different values of omega, x of omega takes different amplitudes. So for all values of omega, if x of omega takes only finite values, for all values of omega, which means x of omega equal to 1, x of omega equal to 2, x of omega equal to 10, x of omega equal to 20, x of omega equal to minus 100. For all values of omega, x of omega should be finite only. If that happens, then only we say that x of omega is well-defined Fourier transform. Is that okay? Now I have explained what is well-defined Fourier transform. The Fourier transform, if this function, if you plot this function, it should not take infinite kind of values. It should not take infinite kind of values, like impulse. If impulse is there, impulse height is infinity. Continuous impulse height is infinity, right? that kind of impulses should not exist. Impulses should not exist. So if the signal is going like this, it will go to infinity, right? At omega equal to infinity, it will go to infinity. This kind of things should not be there. So some infinite values with the help with the presence of impulse, or without impulse also, infinite values are possible. These kind of values should not be there. Only then we can call it as well-defined signal or well-defined Fourier transform. Is that okay? Real time does not exist. What do you mean by that? Satish. Hi Satish. I'm from Andhra Pradesh. Okay, so this kind of infinite values, if they are not existing in a signal, we call that signal as well-defined signal. And if that signal is Fourier transform, if that signal represents a Fourier transform, then that Fourier transform is also well-defined. Okay, but if these kind of values, one infinite value is possible at one place, at omega equal to 10 or omega equal to 20, one place if infinite value is there, one infinite value is there, then we can say it is not a well-defined Fourier transform. Okay, right. So condition for well-defined Fourier transform. Now let us come back to the condition. Yeah, go ahead, Satish. But I have to answer in English, okay? Because others also have to understand, right? So condition for well-defined Fourier transform is, what is that? Absolute integrability. I have discussed it in previous slide also. Absolute integrability is the condition for well-defined Fourier transform. So this should be, if you take the modulus of the signal and integrate it, modulus of the signal area, if you find, that value should be finite. If this happens, then only Fourier transform will be well-defined. Understand this condition. This is very, very important. Based on this only, we will understand ROC. ROC is completely depend on this absolute integrability. So we call this condition as absolute integrability condition. If the signal is absolutely integrable, it will satisfy this condition. Absolute integrability condition. If a signal is absolutely integrable, it will satisfy this condition, which means if you take modulus and find the area, it will give you a finite value. It will give you a finite value. If it does not give you a finite value, if you find this result, take the modulus and integrate. If that result turns out to be infinity, then it is not absolutely integrable. Okay? Right. Understand this condition. It's very, 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 very important. Okay, right. So we've understood the condition for well-defined Fourier transform. So I'll give you a commonsensical understanding of why this condition came. Okay, see this one. It is like finding. Let's assume x of t is having only positive amplitudes. Then if you take the modulus or not, it will be same. Okay, we are talking about signals with positive as well as negative amplitudes also. This is whatever we have talked about here. It is applicable for all kind of signals. But here, just for understanding's sake. Take x of t, which is having only positive amplitudes. Then if you take modulus or not, it is same, right? If you take modulus also, it will be same signal. Let's assume. Let me take a simple case. If that signal with only positive amplitudes, if you take it modulus or not, it will be same. So which means if you're trying to find the area here, you're trying to find the area of the signal. Okay. If you find the area, it should be finite. If you find the area, it should be finite. Then what happens? Try to understand this. Try to understand the value of this Fourier transform at omega equal to 0. If you evaluate this signal at omega equal to 0, it is integration from minus infinity to plus infinity. X of t into e power 0 is 1. So Fourier transform at particular value omega equal to 0. The Fourier transform has a lot of values at omega equal to 0, omega equal to 1, like that infinite values of omega. We are having this signal. Try to understand it at one value of frequency. At omega equal to 0, if you evaluate, its value turns out to be area of the signal. If the signal satisfies this condition, only then this value will be finite, right? If it does not satisfy this condition, which means area is infinite, which means at omega equal to 0, you'll have infinite value, which is an undefined value. Can we say that it is not well defined? If this condition is not satisfied, which means area will be infinity, which means this value will be infinity, which means in Fourier transform at omega equal to 0, at one instant, at one frequency, we are having the Fourier transform to take infinite value if this condition is not satisfied. Correct or not? That is what we are talking about now. Condition for well-defined Fourier transform means the Fourier transform which does not take infinite values. So if this condition is not satisfied, definitely this value will be infinity. Right? Right. If this condition is satisfied, this value will be finite. Not only this value will be finite, for other frequencies also it will be finite. Okay? I hope you're following. So that is, you can understand it in a common sense level. Why you got this condition. You don't need to by heart this condition. It's a very basic condition. In the signals and systems, this condition is repeated multiple times in multiple topics. In Fourier transform, we learn it. We use this condition, absolute integrability. In stability of systems, we will use this. In Laplace transform also, we will use this. In a lot of topics, we will use this condition. Very important condition. Right, let me move on to the next slide. So we have understood condition for well-defined Fourier transform. Whatever we have learned here, same thing we are going to apply for Laplace transform also. Let's learn. So Laplace transform ROC using Fourier transform condition. Right. Let me write whatever we have learned in the previous slide. Using that, we'll learn about Laplace transform condition also. This Fourier transform is well defined. Well defined means it will not take infinite values. For all values of omega, this will not take infinite values. See this one? It's well defined if x of t, instead of writing this, I can also write it as if x of t is absolutely integrable. If x of t is absolutely integrable, then definitely the Fourier transform is well defined. Now, let us write what we have to understand now. From this only we are going to understand everything about ROC. Observe carefully. Integration. So what are we learning now? What Laplace transform are we going to learn? In signal systems, we learned about bilateral Laplace transform. Bilateral Laplace transform. Okay. Whatever formulas you remember in signal systems, they're all bilateral Laplace transform. Because we use the lower limit as minus infinity. We evaluate the transform for all time, for positive and negative time. Okay. So in signals and systems, we also talk about unilateral Laplace transform as a separate topic for the sake of understanding a few concepts like initial value theorem, final value theorem. So to understand a few things, we'll talk about unilateral Laplace transform as well. But using bilateral Laplace transform, we can find unilateral Laplace transform easily, very easily. So Laplace transform formula, I'm just writing. Observe this. So Laplace transform. See this one? The formulas are similar. They're not same. They're similar. Now I'm asking you the question. Same question as the previous one. We know the Fourier transform existence condition, right? Similarly, can you tell me the Laplace transform existence condition? Oh, sorry, not existence. Well-defined condition. Laplace transform is well-defined. Under what conditions? If this is the question. If we can answer this question, it means we have understood ROC. Whatever we are going to get here, whatever is the condition that we get here, that is the condition for ROC. Let's understand it carefully. So whatever we have understood here, since these two are looking similar, let's try to understand the condition for this using this one. Is that okay? So let's rewrite this. Integration from minus infinity to plus infinity. X of t into e power minus, what is s value? S is not same as j omega. If s is same as j omega, Fourier transform and Laplace transform are same, then there is no point of learning two different things. Learning same thing with different name, right? So s is not j omega, s is sigma plus j omega. S is sigma plus j omega. So s and j omega are different. So s has internally j omega, but s is not same as j omega, s is sigma plus j omega. Okay. When you put sigma equal to 0, then only S becomes j omega. Okay. So S is replaced with sigma plus j omega. Now understand carefully. You have to focus very carefully. Limits from minus infinity to plus infinity, x of t. See this one? Let me divide this into two parts. E power minus sigma t into e power minus j omega t dt. See this one? Is it not looking like a Fourier transform formula? But in place of x of t, you are having e power x of t into e power minus sigma t. So, okay, can you tell me the Fourier transform of x of t into e power minus sigma t if you write? What do you write? Integration from minus infinity to plus infinity. For what signal you want to find the Fourier transform? You write that. This is the signal you want to find the Fourier transform for. So multiplied with, for this signal, if you are finding Fourier transform, you are multiplying that signal with e power minus j omega t and then integrate. So for this signal, if you want to find Fourier transform, write that signal, multiply with e power minus j omega t, and then just integrate. Are these two same? Right? These two are exactly same, right? So can I write it as Fourier transform of x of t into e power minus sigma t? Is that okay? So Laplace transform of x of t. Laplace transform of x of t or x of s is same as Fourier transform of x of t into e power minus sigma t. So Laplace transform of x of t is same as Fourier transform of x of t into e power minus sigma t. Is that okay? Have you observed this? So Laplace transform or Fourier transform of a signal not exactly same, are not same. They're different, but this is the relation between Fourier transform of a signal and Laplace transform, Fourier transform and Laplace transform relation. So for the signal, if you multiply e power minus sigma t and then find Fourier transform, it is exactly same as Laplace transform. So what is the point of getting this? Sir, we got this relation. How is this going to help us? See, this is the question that we want to answer, right? So Laplace transform, we have expressed it as Fourier transform. With the help of Fourier transform, we know the condition for well-defined Fourier transform. The condition is absolute integrability, right? Since we are trying to look at Laplace transform as Fourier transform, since we are trying to look Laplace transform of x of t as Fourier transform of x of t into e power minus sigma t, okay? So let us understand the condition for this. So under what conditions this Fourier transform will exist? Can you tell me? Under what conditions this Fourier transform will exist? Very simple question. Fourier transform of a signal is well defined. Fourier transform of a signal is well defined if it is absolutely integrable, correct? And Fourier transform of this signal is well defined. Fourier transform of this is well defined if x of t into e power minus sigma t is absolutely integrable. Absolutely integrable means apply modulus and integrate. If this signal is satisfying absolute integrability condition, not x of t, absolute integrability of not x of t, absolute integrability of x of t into e power minus sigma t. If x of t into e power minus sigma t is absolutely integrable, then Fourier transform of this is well defined, which means it will not take infinite values. Okay, if this is well defined on the right hand side, if the right hand side is well defined, left hand side also will be well defined, correct? So Laplace transform of x of t is well defined, which means it will not take infinite values when it satisfies this condition. When this is well defined, this also will be well defined. Well defined means not taking infinite values, not taking plus or minus infinite values. If this does not take plus or minus infinite values, this also will not take plus or minus infinite values. If this is well defined, this also will be well defined. When is this well defined? This is well defined only when x of t into e power minus sigma t is absolutely integrable. Under this condition, this will be well defined, this also will be well defined. So Laplace transform x of s is well defined if x of t into e power minus sigma t, if this signal is absolutely integrable. That is the condition. whatever we have written here, that itself is ROC. Okay, we'll talk about it. We'll talk about it in detail. But this is the core part that we have to understand. Have you understood till this point? Laplace transform is well defined. What does it mean? Laplace transform does not take any infinite values for any value of s. For s equal to 0, 0 plus 1, 0 plus j1, s equal to 2, s equal to 3. For any value of s, x of s is never going to be infinity. That is what I mean by well definedness. Okay, so for x of s to be well defined, this is the condition that should be satisfied. Okay, now let us deep dive into this condition. Then we will understand about ROC. Okay. See this one? Now I'm defining ROC. ROC means region of convergence. Why do we call it as a region of convergence? Region means it is some in a plane. If you plot some region, that is what we call as region, right? Yes, there is a reason why we call it as a region of convergence. Okay, we'll talk about it a little later. But ROC is the range of values of s for which Laplace transform is well defined. Try to understand this. The values of s for which the Laplace transform is well defined, or values of s for which this condition is satisfied. This condition is not, this condition x of t into e power minus sigma t need not be absolutely integrable for all values of sigma, right? For some cases it might happen, but for many cases, for all values of sigma, this signal will not be absolutely integrable. We'll take some examples and see. For all values of sigma, this signal is not absolutely integrable, which means for certain values of sigma, this satisfies absolutely integrability condition. For certain values of sigma means only for certain values of s, because as sigma is part of s now. For certain values of s only, this Laplace transform is well defined, not for all values of s. This Laplace transform need not be well defined for all values of s. The values of s for which, or the values of sigma for which this Laplace transform is well defined, only for those values of s for which it is well defined, we call it as region of convergence. Instead of region of convergence, you can also call it as range of values of s for which it is convergent. So the meaning of convergence is finite values. If the Laplace transform is having finite values, then we say it is convergent. Okay, convergent represents finite. Okay, we'll talk more about it. Okay, observe carefully. Right. Now let us understand carefully. X of s. Let me write the Laplace transform. Integration of x of t into e power minus st dt. This is the Laplace transform condition. Formula. Limits from minus infinity to plus infinity. Laplace transform is well defined, or defined, or well defined, you can say. Is well defined if this is the condition that we have written in the previous slide. Now let us learn it in more detail. It is well defined if this condition is satisfied. Is this condition satisfied always? Is it satisfied always? Is it satisfied for all values of omega? For all values of omega, is it satisfied? Is it satisfied? Yes, no? Anyone? Is this condition? Can you guarantee that this condition will be satisfied for all values of sigma? Okay, sigma is some variable which is part of s. S is a variable. Inside s there are two parts, sigma plus j omega. There are two variables, sigma and omega. In Fourier transform there is only one variable, omega, whereas in Laplace transform the variable is s. Internal to s there is real part and imaginary part. So sigma and omega both are variables. Since sigma is variable, it can take all the values from minus infinity to plus infinity. So this condition, can you guarantee that this condition will be satisfied for all values of sigma? The answer is need not be, right? Need not satisfy. It need not be. it is based on the signal x of t. What signal you take, what signal you take in place of x of t, based on that, for all values of sigma also it might be satisfied. For certain values of sigma it might be satisfied. For no value of sigma also it may not be satisfying. Okay, it depends on x of t sigma. Okay, we'll take some examples. Okay, if you take del of t here, then if you take del of t here, this part is finite always. So if x of t is del of t, for all values of sigma it is satisfied. If x of t is u of t, then this condition is satisfied only for some values of sigma. If x of t is u of minus t, then this condition is satisfied only for certain other values of sigma. Okay, so this condition is not, most of the time this condition is not satisfied for all values of sigma. It is only satisfied for certain values of sigma. Okay, so the values of sigma for which x of t into e power minus sigma t is absolutely integrable. See this one, the values of sigma for which x of t into e power minus sigma t is absolutely integrable, which means the values of sigma for which this condition is satisfied, the values of sigma for which this condition is satisfied is the values of sigma, the same values of sigma for which this condition is satisfied, is the values of sigma for which Laplace transform is well defined, correct? Because Laplace transform is well defined when this condition is satisfied, and this condition is not satisfied for all values of sigma. This condition is satisfied only for certain values of sigma. Those certain values of sigma for which this condition is satisfied, only for those values of sigma, Laplace transform is also well defined. So these values of sigma for which this condition is satisfied, those values of sigma, we call it as region of convergence, or range of convergence also we can call it, but somebody has coined the word region of convergence. There is a reason why they have coined it as region of convergence. The reason is, whatever values of sigma you're talking about, those you can plot on a graph. So for example, S is the variable here. So we take an S plane. S plane means we plot real part of S on x-axis, which is sigma. Real part of S means sigma on x-axis, and imaginary part on y-axis, imaginary part of S on y-axis, which is omega. Okay. So if you try to plot, so S means S represents a particular point, right? S represents a particular point. So in that point, S has sigma plus j omega, it has real part and imaginary part. So different values of S, for different values of S, Laplace transform might be well defined or may not be defined also, right? So different points in this plane represents different values of S. Okay. So we are talking about different values of sigma. The values of sigma for which Laplace transform is well defined, that if you plot it in this graph, those values of sigma, they represent different points on the plane. For example, let's say sigma greater than 2 is the range that we are talking about. For example, I have given you some signal, and I found that for sigma greater than 2, this condition is satisfied. Then if for sigma greater than 2 means, let's say this is sigma equal to 2 line. Sigma greater than 2 means it represents this total region. So this total region, for this total region, Laplace transform is convergent, or Laplace transform is well defined. So that is why the name region of convergence. Okay. If you talk about as value in a range of values, then region does not make any sense. Okay. But if you plot it as a graph, the values of sigma, whatever you're talking about here, that if you plot it as a graph on X plane, that represents a region, the region of values. So that's why the name region of convergence. Is it clear till this point? Is it clear till this point? In this slide, I've explained the most important part, which is region of convergence. Whatever we've talked about in the previous slides is the basics to understand this. If you have any doubt, you can let me know. Any doubts, anyone? Anything not understood, you can let me know. I can explain it once again. It has to converge from 0 to infinity. It need not be, Vaibhav. We'll take some examples for some signals, then you'll understand it more clearly, okay? If still there is a doubt, you can ask me. Based on the signal, if x of t is different, the values of sigma for which this condition is satisfied also will be different. For different signals, this condition is satisfied for different values of sigma. Okay, once we take example, things will become more clear. But this is the idea. This is the idea behind region of convergence. Right. Now ROC of Laplace transform, region of convergence of Laplace transform. So I have written the condition here. The values of sigma. Sigma means sigma is part of S, which means the values of S also we can call it. Okay. The values of S or values of sigma for which x of t into e power minus sigma t is absolutely integrable. Those are the values of sigma for which Laplace transform is well defined. Okay, or Laplace transform is existing, we can call it. Right. So let us talk about a little bit more about ROC of Laplace transform. So let me take a signal. X of t equal to u of t. Let's take this signal, or let us take the very basic signal. Let's start with our favorite signal, whose transform is easy to remember, del of t. Okay. Now, let us find the Laplace transform of this one. X of s is equal to integration of x of t into, in place of x of t, let me substitute del of t into e power minus st dt, which is equal to, since impulse is there, so impulse exists at t equal to 0. In the neighboring signal, substitute t equal to 0. Whenever impulse is there, it's easy to evaluate. Okay, so impulse exists at t equal to 0. So substitute t equal to 0 in the neighboring signal, it will become e power 0, which is 1. Then integration of impulse will become 1 unit. So Laplace transform, okay, especially bilateral Laplace transform of del of t is 1. If you take unilateral Laplace transform also, 0 to infinity also, then also it will become 1. Right. But the most important part is not finding the Laplace transform. In signals and systems, the most important part is not finding the Laplace transform. Finding Laplace transform is also important, but the most important part is finding the region of convergence. That is the most important part. Because in mathematics, whatever you deal with is unilateral Laplace transform. There's region of convergence is not mandatory to find. In bilateral Laplace transform, without region of convergence, your answer is not complete. Half of your answer is region of convergence. It's not just the Laplace transform. Okay. So this is the Laplace transform. For what values of sigma this is valid? For what values of sigma, this is the answer. For what values of sigma, this is the Laplace transform. We have to find that. For values of sigma which satisfy, for values of sigma which satisfy absolute integrability condition. So now let's figure out what values of sigma this condition is satisfied. Now we have given you the signal. Now there will not be any confusion. Let's substitute that signal. Whatever signal we are talking about, that signal we have to substitute here. Since this signal is positive, you can remove the modulus also. So what is the value of this one? We have just now evaluated. Impulse is there. Impulse exists at t equal to 0. Substitute in place of t, substitute 0 in the neighboring signal. So it will become 1. So is 1 always less than infinity? This is correct now. For what values of sigma this condition is happening? This condition for impulse signal, is it happening for what kind of values of sigma is it happening? For all sigma, right? If you put sigma equal to 0, minus infinity, plus infinity, for any value of sigma, this condition is being satisfied. Correct? So for what values of sigma this condition is being satisfied? For all values of sigma. So Laplace transform of del of t, we know the Laplace transform is 1, but this answer 1 is valid, need not be valid for all values of sigma, but in this case for impulse signal it is valid for all values of sigma. For all sigma you can write, or you can also write it as minus infinity less than sigma less than infinity. Instead of this you can also write as for all sigma. Is that okay? For this particular signal, For all values of sigma, this absolute integrability condition is satisfied, which means for all values of sigma, the Laplace transform is well defined and it exists. Similarly, let us take the second example also. Let us take x of t equal to u of t. Understand carefully. So before talking about this, let me ask you some questions, okay? Let me ask you some questions. E power j infinity, e power j infinity and e power infinity. What are these values? Can you tell me? What is e power infinity? It is very clear that it is infinity, correct? What is e power j infinity? Magnitude of it. What is the magnitude of it? Anyone? Because this is complex, no? This is complex. J is there in the power, so which means it is complex. When it is complex, it will have real part and imaginary part. That's why I'm interested only in the magnitude. Here also you can talk about magnitude. What is the magnitude of this? When j is there, e power j infinity does not become infinity, it becomes only 1. Because it is like cos infinity plus j sin infinity. When you're talking about modulus, it is cos square plus sin square. Cos square plus sin square is always 1 irrespective of the argument into it. Correct? So when j is there, magnitude need not be infinity. Mind this. Similarly, e power minus j infinity, what is the magnitude? It is again 1 only. E power minus infinity, without j, it will become 0. Correct? When you raise to the power, in the power if there is j or there is no j, you have to be careful. If there is j, magnitude is 1, irrespective of what is beside j, irrespective of what is beside j. Beside j, if there is infinite value or finite value, it does not matter, magnitude will be 1. Okay, right. So e power a plus jb, e power a plus jb in this, if you take the modulus of this, what decides the modulus? E power a, we can write as e power a into e power jb. E power jb modulus is 1, so it becomes only e power a. So when you take an exponential signal or number in the power, what decides the magnitude is a real part of the power. Mind this, the real part of the power decides the magnitude. Imaginary part also has significance, but when you're calculating magnitude, only the real part has significance. Okay, I hope you're following. Right, now let us come back to the question. So this implies x of s is equal to integration of u of t into e power minus st dt, limits from minus infinity to plus infinity, which is equal to, since u of t is there, u of t exists only for positive time, the equation of u of t is 1 only for positive values of time, only for values of time from 0 to infinity. For other values of time, the equation is 0. So this is equal to minus 1 by s into e power minus st, limits from 0 to infinity. Mind this, try to understand this carefully. Sometimes ROC we can find it directly from this evaluation itself. Minus 1 by s into e power minus s into infinity minus e power minus s into 0. Observe carefully. Minus 1 by s into e power minus s into infinity minus e power 0 is 1, which is equal to 1 by s. This part minus 1 into minus 1 by s is 1 by s minus 1 by s into e power minus s into infinity. See this one? Sir, we have learned it as 1 by s, but you are getting some different answer. Yes, try to evaluate. Let's try to evaluate this. Let us try to evaluate this. Understand carefully. So let us understand this one. E power minus s. Yes, can we replace it with sigma plus j omega? Because s has real part and imaginary part. From our discussion previously, only the real part decides the magnitude. Correct? So when you multiply with infinity, it is e power minus sigma into infinity plus e power minus j omega into infinity. Sorry, into, right? Power, See this one? E power minus sigma into infinity. If you want the modulus, only the modulus. We are interested in the magnitude. So the magnitude of this is 1. So what decides the magnitude is only the real part of the power. Real part of the power. See this one? Same discussion. Whatever I've done here, same thing here. So is this value can be infinity. When you raise it to the power, it can be infinity or it can be 0. See here, infinity is there, infinity is there. If the power is negative infinity, it is 0. If the power is positive infinity, it is infinite. Right? So, sir, we are seeing minus sign, it should be 0. Come on, there is variable here. Sigma is a variable here. Variable means it takes all the values from minus infinity to plus infinity. Okay? So, if it takes all the values from minus infinity to plus infinity, then sigma is taking positive values as well as negative values. Sigma is not taking a single value. Sigma is a variable which can take all values from minus infinity to plus infinity. So it's not fine, it's not good to say that it is 0 or infinity, because sigma has different values. Sigma can take different range of values. Now let us analyze it for two ranges. If sigma is positive, what happens? And let us also analyze it for sigma negative. If sigma is positive, positive into negative is negative. E power, it becomes e power minus infinity. This value multiplied with infinity is infinity. E power minus infinity becomes 0. Correct? Now, if sigma is negative, what happens? If sigma is negative, something like minus 3, minus 4, minus 5, something like that. This is negative. Negative into negative is positive. Positive into infinity is plus infinity. So, it will be e power plus infinity. If sigma is negative, then it becomes e power plus infinity, which will be infinity. So, based on for different values of sigma, the result is different. So this result, the answer is 1 by s, and this value e power minus s into infinity. This is what is e power minus s into infinity. This value can be 0. This value can be infinity. But what values are we interested in Laplace transform? Are we interested in infinite values? Are we interested in infinite values of Laplace transform? For this one, infinity is also possible. Are we interested in infinite values of Laplace transform? If you get an infinite value, then Laplace transform is not well defined. We don't want that case. We always want the transforms to be well defined. Whether it is Fourier or Laplace or any transform, we want them to be well defined. Okay, right. So for sigma less than 0, it is not well defined. This takes infinite value. We are not interested in that. But for sigma greater than 0, it becomes 0. This part becomes 0. This part becomes 0 only for sigma greater than 0. For only sigma values greater than 0, the Laplace transform is becoming well defined. The Laplace transform is becoming well defined only for sigma greater than 0. Okay, for sigma less than 0, this becomes undefined. For undefined, when you are getting undefined values, there is no point of writing them also. Laplace, when you are writing Laplace transform, we are writing only well defined cases. We are not interested in not well defined cases. So when you write Laplace transform of u of t is 1 by s. If you write this, it is incomplete answer, because 1 by s is not valid for sigma less than 0. For sigma less than 0, the answer is 1 by s. It is not valid, because for sigma less than 0, Laplace transform is not defined at all. We don't write the Laplace transform at all. Only for sigma greater than 0, this is correct. Try to understand carefully. If you write only 1 by s, when you are writing bilateral Laplace transform, if you write 1 by s without this, the answer is wrong. Because for what values of sigma or for what values of s is this defined? Is this answer valid for all values of sigma? No. This answer is valid only for sigma greater than 0. So you have to mention that. Without mentioning this ROC, the answer is incomplete or answer is wrong, I would say. Are you following? See, here we did not use any absolute integrability condition, the condition for ROC. What is the condition for ROC? Without using that condition also, we got it. Many times we get this. Many times when you are evaluating the Laplace transform itself, for certain values it will become infinity. Those values we avoid. Only for values of sigma, for which we get finite values, only those values we take into account. That itself will give you region of convergence. We don't need to use the separate region of convergence condition. Let us use it in this case so that you'll understand it better. So this Laplace transform is convergent only for values of sigma which satisfies this condition. What is the condition? X of t into e power minus sigma t dt. X of t into e power minus sigma t dt. So what is the condition for region of convergence? This is the condition for region of convergence. The values of sigma for which this condition is satisfied, those values of sigma, we call it as region of convergence. In this case, we did not find it. This condition we did not use, but we got it. In the Laplace transform analysis itself, we got it. In most of the cases, we get it that way. Let us substitute and find it, whether we'll get the same answer or not. Well, let's see. X of t, in place of x of t, just substitute u of t. Which is equal to, since u of t is there, limits we can change from 0 to infinity. U of t equation is 1 in that limits. Now tell me, we want this to be less than infinity or finite. We want it to be finite. We want this to be finite. Area of exponential signal, will it be finite? Will it be finite? Yes, it will be finite if sigma is positive, correct or not? If sigma is positive, then it will be an exponentially decreasing signal for positive time, correct or not? If sigma is negative, then negative into negative becomes positive, then it becomes an exponentially increasing signal for positive time, and if you find the area, it will become infinity. Okay, I hope you're following. So if sigma is positive, then this becomes exponentially decreasing for positive time, and if you find the area, it will be finite. Okay, so this becomes finite only for positive values of sigma. For all values of sigma, this will not be finite. Only for certain values of sigma, this will be finite, and those values of sigma for which it is finite, we call it as ROC. So same condition we got here. So many times we don't need to use this condition separately. Okay, that condition we'll get it without explicitly using this. We'll get it by finding the Laplace transform itself if you do it carefully. Okay, right. So similarly, can you analyze for u of minus t? Can you analyze for u of minus t? If it is u of minus t here, or else you can substitute here, u of minus t here. U of minus t means the limits are from minus infinity to 0. Minus infinity to 0. So then the condition will be exactly opposite. Only for sigma less than 0 values, this condition will be satisfied. Instead of u of t, if it is u of minus t, then the condition will be exactly opposite. We'll do that, okay, quickly. Give me a minute. Okay. Let's take x of t equal to u of minus t. Let's analyze. X of s is equal to integration u of minus t into e power minus st dt. Limits from minus infinity to plus infinity. So this is equal to u of minus t exists only for negative time. So the equation of u of t is 1 only for negative values of time. So for minus infinity to 0, the equation of this is 1. And for positive values of time, so I'll divide the limits into two parts. Minus infinity to 0 and another from 0 to infinity. For minus infinity to 0 time, the equation of this is 1. And for 0 to infinity time, the equation of this is 0. Okay. Now this part becomes 0. How about this part? It is e power minus st divided by minus s. If you integrate this, limits are from minus infinity to 0. Let us substitute e power minus s in the denominator. Let's substitute the limits. It is e power 0 minus e power minus s into minus infinity. So this is 1 divided by minus s, or minus 1 by s plus e power plus s into infinity. Minus into minus is plus divided by s. So the answer, the Laplace transform here for u of minus t is minus 1 by s. What is this value? Let's evaluate it. E power plus s into infinity. In place of s, I'm writing sigma plus j omega into infinity. So in this, the magnitude is decided by only the real part of s. E power sigma into infinity into e power j omega into infinity. The magnitude of this part is 1 because j factor is there. So magnitude is decided only by sigma. So for what values of sigma this will become finite or infinite? For sigma greater than 0, what happens? If sigma is positive, positive into infinity is infinity, e power infinity becomes infinity. And for what values of sigma For negative values of sigma, what happens? For negative values of sigma, negative into infinity is minus infinity. E power minus infinity is 0. Say this. This part can become infinity. This part can become 0 based on the values of sigma. What are we interested in? Are we interested in infinite values in Laplace transform? We are not at all interested. If you get an infinite value for Laplace transform for any value of s, we are not interested in that. We say that for that values of s, Laplace transform does not exist or it is not defined. So for sigma less than 0, it is 0. 0 value is completely fine, acceptable. So we can take the value of 0 for this, and that happens only for sigma less than 0. If sigma is less than 0, this part becomes 0. For sigma greater than 0, it becomes, this is infinity. Infinity plus anything is infinity. That infinite values are not acceptable. For sigma greater than 0, this Laplace transform, we say it's not defined. It's not defined, or it does not exist, we can say. Does not exist, we can say, or not defined, we can say. So generally we don't write this, we only write this. It means for remaining values of sigma, Laplace transform is not defined, or it does not exist. We write only this part. We don't need to explicitly write this part. For your understanding sake, I have written in this case. Okay, but when somebody writes like this, writes the Laplace transform for certain values of sigma, it means for other values of sigma, it does not exist. So Laplace transform exists only for certain values of sigma, not for all values of sigma. That values of sigma for which it exists, we call it as region of convergence. Okay, so for this one, if you plot it, if you plot the region of convergence, let me take the S-plane, sigma on x-axis and omega on y-axis, if you take. So let us plot the values of sigma less than 0. For all points, sigma will be negative. Sigma is real part. Sigma is negative means it represents all this part. The second quadrant and third quadrant, all of them represents, all points in the second and third quadrant have a negative value of sigma, correct? So let's plot, whenever they talk about sigma less than 0, if you want to plot this region, first plot sigma equal to 0. And sigma equal to 0 means it is like x equal to 0 line, it is like y-axis. So sigma less than 0 means it represents this region, this total region. Like that, whatever ROC we get, we can plot it as a region as a region on a graph on S-plane. S-plane graph, if you plot the region of convergence, whatever you get here, that if you plot it, we get it as a region. So that's why for this region of values of sigma, the Laplace transform is convergent. The Laplace transform is defined, well defined. Okay. Similarly, for the previous case, if you plot ROC, it is sigma greater than 0, which means this is sigma equal to 0 line. Sigma greater than 0 means it is first and fourth quadrant. For all the values, for all the points in first and fourth quadrant, sigma is positive. So it represents this total region. Okay, similarly, for the first case, if you plot ROC on an S-plane, sigma on x-axis, omega on y-axis, for all values of sigma it is defined. So which means you can plot the total thing. For all values of this total region, the Laplace transform is well defined. Is it clear till this point? Everyone? Right. So tomorrow we'll discuss the Laplace transform of some important signals. Whatever signals we come across most of the time, for those signals we'll find Laplace transform. Okay. We might take the help of some properties as well. Okay. Right. So I've given you some simple homework. I'm asking you to find the Laplace transform of del of t minus 2, u of t minus 2 and u of minus t minus 2. So don't use any properties because I've not yet discussed any properties. Let's go with whatever is discussed till now, which means I'm asking you to use only the Laplace transform formula that I've given you. Use the Laplace transform formula that I have given you. Don't use any properties because I want you to understand the basic meaning of Laplace transform and its region of convergence by using the basic formula. Say this one, this formula is what you have to use. Minus st. Just use this formula to find Laplace transform and region of convergence. Without region of convergence, the answer is incomplete. Is that okay? So region of convergence, when you're evaluating this formula itself, you'll get the region of convergence. But if at all, if there is a confusion about region of convergence, you can use the region of convergence condition. What is the ROC condition? ROC condition is, region of convergence condition is, if at all, if there is a confusion only, then use this condition. Otherwise, you get that ROC from this Laplace transform analysis itself. This is the condition for ROC. Yeah, sure, Rahul. I'll share the PDF in Telegram, definitely. Okay. So using this formulas only, I want you to find the Laplace transform of these three signals. You should find the ROC as well. So tomorrow, first thing, I'll discuss the answers for these questions. I want very specifically, I want the ROC exactly correctly. Okay. So there is a chance of making mistakes in the ROC part. The other part, you might be doing it correctly. The Laplace transform, you might find it correctly, but ROC part, there is a chance of making mistakes. Don't make those mistakes. Okay. So in the next classes, we'll discuss properties. With the help of those properties, we can find the answer for these questions in very, very easy way. Just like few seconds it will take. And the ROC also we can find it easily. But this is the basic from which we have built those properties also. All the future classes, whatever we are going to learn, that is based on this basic only. This is based on this only, we have built all that. So we should not forget the basics. If you forget the properties also, that's fine. You should not forget the basics. So this is the core part. So this class, whatever we have understood is very, very important. If there is any confusion, go through the class once again. Wherever you got confused, that part of the class, you just listen to it once again. Become perfect in that. After that, any question in Laplace transform will be easy to understand. Okay. So shall we stop at this place? So don't forget to answer these three questions. And I want you to post it in the comment section. If you have done it correctly, and if you are confident about your answer, then post it in the comment section. Okay. I'll know that you have done it correctly. You have understood the class correctly. Okay. Fine then. So if you have not subscribed to our channel, you can subscribe. And if you like the session, don't forget to press the like button. Okay. So shall we stop at this place then? So you can copy the questions. Okay then. So I'm stopping the session. So we'll meet again in tomorrow's session. Same time, 8 o'clock, 8 a.m. Okay. Thank you.